evening, sir. Hello, classmates. This is Vivian. I will show to you our solution to problem number 6. The problem states that let X bar and matrix A be based on a sample of size n from a p-variate normal distribution with mean the mu vector and covariance matrix sigma. Let the X vector be an additional observation from a p-variate normal distribution with mean the mu vector and covariance matrix sigma independent of the sample. Show that n times n minus 1 over n plus 1 multiplied to x vector minus x bar vector prime times the inverse of matrix A multiplied to x vector minus x bar vector has the distribution of Hotelling's t-squared. Here is our solution. This is a two-sample problem. Let x bar upper 1 and x bar upper 2 be the sample means of the first and second samples, where x bar upper 1 is from the additional observation from p-variate normal with mean mu and covariance sigma. X bar upper 2 is from the sample of size n from p-variate normal with mean mu and covariance sigma. But x bar upper 1 is the x vector, which is the mean of the additional observation, and x bar upper 2 is x bar, which is the mean of the n sample. Define the normal vector as x bar upper 1 minus x bar upper 2, which is equivalent to x minus x bar. Next, derive the covariance matrix of the normal vector. So the variance of x minus x bar is equal to the variance of x plus the variance of x bar. Variance of x is sigma plus variance of x bar is 1 over n times sigma. This simplifies to n plus 1 over n times sigma. Sigma is a population parameter. We need to derive its unbiased estimator. From our course notes on page 23, we find that the sample covariance matrix S is equal to matrix A over n minus 1. So, we get the expectation of S. Substitute A over n minus 1 for S. Note that the characterization of A is the summation of z alpha prime, where alpha is from 1 to n minus 1. Note further that z alpha is independent and identically distributed p-variate normal with mean the zero vector and covariance sigma. After doing the math operations, we get sigma. Hence, the unbiased estimator for n plus 1 over n times sigma is given by n plus 1 over n times S. Now we build the Hotelling's t-squared. The first term is the transpose of the normal vector multiplied by the inverse of the middle term, which is the unbiased estimator of the normal vector's covariance matrix, then multiplied to the normal vector. Recall that matrix S is equal to matrix A over n minus 1, which we substitute for S here on the second line. The inverse of the constants on the middle term is n times n minus 1 over n plus 1. Placing the inverse of the constants in front, we arrive at n times n minus 1 over n plus 1 multiplied to the normal vector transpose times the inverse of matrix A multiplied to the normal vector. Thus, we have shown that this last line has the distribution of Hotelling's t-squared. This concludes the solution to problem number 6. We welcome your comments or questions. Thank you for your attention.